Today we're going to look at, I and my colleague here, his name is Justin Murray, he'll also be presenting. The reason we have Justin here today is he focuses on big data, I focus on HPC. Now all of this is coming together. He'll talk to, so that we actually both share the ML responsibility inside VMware. So, this is not flipping?
No, you have to, it's manual.
It's manual, okay.
Unless you brought your own.
Okay. So there are, as you see, there's a huge transformation happening in IT. So we talk about on-prem versus off-prem, versus public versus private cloud. One area, particularly HPC, has been pretty dormant in the sense it's still like 80 to 90% of all the workloads are on-prem and they're bare metal. The reason being, performance is always attributed to, any loss in performance is not acceptable and stuff like that. But if you look at what's happening in the public cloud arena and a lot of things with Amazon and Azure and Google Cloud, there are a lot of workloads moving there. And the first thing I want to remind everyone is all these public cloud environments are virtualized. So there's no argument about performance when you go to public cloud, but when you go back to on-prem, we always talk about performance. So what we will talk about today is how can you make your on-prem HPC agile and performant and just like agile and productive for your users and engineers, just like your public cloud is. So the reason the shift is happening is, why are they moving? They're moving because of the agility and the ability to scale and stuff like that. And so that's kind of what we'll look at. So you look at all these technologies out there. There's all these things in the bottom you see, like there's GPU, there's FPGA, PMEM, all these new technologies are coming out, right? So it's very hard for static environments to keep up with it. That means as a new hardware comes in, all these capabilities are there, but if you have, if you kind of buy bare metal hardware and kind of dedicate it to one project, you're stuck. You're not able to use all the latest and greatest things. So that's kind of what we see. So what we see is the fact that infrastructure is no longer can be static. It needs to be dynamic. You need to be able to adapt to it. And from a VMware standpoint, we kind of make the infrastructure, be shared across multiple groups and multiple departments and stuff like that, with all the bells and whistles you would require, and that way you are actually not stuck or dormant, right? And so one of the important thing I want to mention is security, right? A lot of these traditional HPC environments, the data cannot be shared, so the infrastructure is always has air gap. You really have a separate lab for this department versus another department. And if you go to the public cloud arena, they give you your own virtual private clusters and all that, but on the back end, you're actually sharing the hardware. And they do it logically, and so the same kind of capability you can have in the private cloud space as well. And by doing that, you're actually sharing the hardware, but not dedicating hardware, right? So kind of, I just wanted to reiterate what we said. We want to be able to increase the agility of HPC environments on-prem, which is not the case right now. You want to be able to efficiently allocate and manage and ensure compliance and all that. But at the same time, we want to bring in what virtualization is very useful for. As you know, VMware is a company that's been there for 20 years. We are in the enterprise IT space, not as much in the HPC space. But a lot of the technologies that we provide with virtualization can be applied to HPC to make it agile. So that's kind of what. So now, why do we want to virtualize HPC environments, right? So it gives you operational flexibility. So these are the common things that you hear in the public cloud world as well. It gives you operational flexibility, there's reduced complexity, and then you're able to secure, you're able to share the environment, but at the same time, you're able to secure different groups from seeing each other's data, but at the same time, they're running on the same hardware. So that's kind of, so The next thing I want to talk, since this is talk about machine learning and accelerating, I'll just talk about GPUs and one common myth that people have. The myth is that virtualization is a layer that is on top of the GPU. It's going to slow you down. That's not true. So you see this. You see that there's a 4% degradation. But we have worked with NVIDIA, and NVIDIA has a product called NVIDIA Grid. We are actually literally passing the guest directly to the hardware. So there is no hypervisor that's kind of splitting things here. So the software that is used for sharing GPUs are provided by NVIDIA. And so it's not, VMware is not a layer in between. So there's no performance impact. So because you guys are very performance sensitive, I just want to bring that. So I'll pass it on to Justin, who's going to talk about the ways you can use GPUs in VMware, and then I'll come back.
Thank you, Mohan. Good afternoon, folks. I'm going to pull back a little bit here and give you a broader landscape of VMware looking at these fields of big data, machine learning, and HPC, and how they all relate together in our minds. So you can think of the entire collection here as HPC, and the individual parts within it made up of machine learning, traditional data analytics, big data as in Spark, Hadoop, etc., and then deep learning as a subset of machine learning. How do we address all that? Well, I won't go into training and inference. That's pretty much understood by this audience here. I'm frequently in the business of explaining this to newcomers in our customer base who are probably used to big data but not quite used to machine learning yet. So the way we see it, as my colleague mentioned, was we do a lot on premises. That's been our history. We're also looking at cloud now, and we have an offering in the cloud. We think these things, all of them, will take place in both environments. They won't be exclusive. There'll be parts that are done in both. There might be the full life cycle done in both. So training will come either from cloud-based big data or on-premises big data or other sources, classic databases, data analytics, that will feed into machine learning, and that will produce inference that may be deployed on-premises, may be deployed on the cloud. We want to be agnostic to these two environments. In fact, we've already built prototypes of doing inference on-premises and transporting the model to the cloud, or vice versa. Doing training in the cloud and transporting the trained model, the coefficients, down to on-premises. And this leads us to think about the edge, or IoT, where a lot of data is being generated at a factory floor, on retail locations, huge amounts of data being generated. Those, of course, are going to feed back into training via some other platform, like a Spark platform for cleanup, for data preparation, for feature engineering. You might use Spark for that, for example, and then feed back into the on-premise, the edge site, which will be a place where you want to do inference particularly, and maybe even some parts of the training. So we see this as an integrated landscape. We want to play in all of it. We're already playing in on-premises, and we have, as I said, VMware software running in the cloud now. It's called VMware Cloud on AWS, running on bare metal AWS servers that we're doing some parts of this in as well. All of that could be viewed through a lens which is not your traditional disk-oriented laptop. It's through some device that retains the data in the data center for security purposes, as my colleague said. We can secure the virtual machines in the data center. We're not so sure we can secure the data on your laptop. That might get taken in the backyard or something like that. So VDI, virtual desktops, is one way of not giving the data scientist a laptop-based copy of your data. The data stays in the data center, but they get access to the data over the network effectively. Not total security, but one form of it. So reflecting back on what my colleague Mohan said, there is GPU support on VMware virtual machines to begin with. As he said, virtualization underpins a lot of the public cloud. For us, it underpins all of the private cloud now. Something like 60–70% of the workloads in data centers is now virtualized, and a large portion of that is running on our hypervisor. We see three different types of requests coming towards us, and this is why I asked the question earlier, how many GPUs are data scientists really using? We want to be able to supply one full GPU to a single user on the far left-hand side, a single user, a single VM. We want to be able to supply multiple GPUs to one user. That's the middle column. And that's 4, 8, or however number of GPUs that particular data scientist needs because they're doing distributed training or they're doing high-end training. We want to enable that as well. We have enabled it. And we see use cases also that may be less familiar to you of people saying, well, I bought these GPUs, I bought 8 or 16 of them, but I really want to share them among 2 departments. I don't really want to dedicate any one GPU to one particular person. That's the idea of breaking up a GPU into 2 pieces and allowing somebody to use half of the GPU for a period of time, somebody to be able to use the other half at the same period of time. We call that GPU virtualization. We call these virtual GPUs, which actually represent a share in the real physical GPUs. And you'd be surprised at the number of enterprises and even research organizations that are interested in optimizing, from our title here, optimizing the use of machine learning that way. As you see on the bottom, there are actually just 3 methods there. There are direct path I/O, using NVIDIA Grid, which is a virtualized GPU product from NVIDIA in software, and using a product called a Bitfusion FlexDirect, all of which runs on top of the hypervisor, and some parts run in the hypervisor on VMware. VMware actually comes out of Stanford. Professor Mendel Rosenblum and his wife founded VMware from Stanford about 20 years ago. So there's a proud connection between VMware and Stanford. So direct path I/O, very briefly, is the ability to transmit the instructions from the driver, this CUDA library and the GPU driver, directly through the operating system in the VM, down through the hypervisor into the GPU hardware in a direct fashion with no intervention by the hypervisor. We call that direct path I/O or pass-through. And effectively, we're passing through all the GPU-specific instructions from the driver without touching them. And this is going to bring you within 3 to 4% of the performance of the physical equivalent, the same machine with the same GPU. We're going to come in with a performance hit of about 3 or 4% on that. And we've measured this very carefully, and we have white papers on this subject that we can give you that are careful measurements of this. So that's the simplest form. That GPU then is dedicated to that VM. We don't share it. We don't move it. If you may know VMware, we're very fond of moving virtual machines around in the data center between different host servers. We call that vMotion, to do load balancing across the data center so that no one machine is overloaded. Instead, we have a balance across the data center. Well, we turn that facility off in this case because we're going to keep that virtual machine on that host for its lifetime. And you can do multiple GPUs this way if you want to, and this is quite a feasible way to do it. Multiple GPUs are assigned to that VM. That VM is going nowhere. It's staying where it is. And that's what I mean in the caveat section when we say no vMotion. No suspend and resume I'll get to in a minute. That's the concept of stopping a VM for a period of time, using the hardware for some other purpose, some other VM's purpose, and then resuming it like a virtual desktop that you might suspend at 5 o'clock because your workers have gone home, and do training overnight, and then come back in the morning and restart or resume that VM. That facility is not there with direct path I/O. So it's got limited sophistication in the virtualization context, but it does serve the purpose of giving you 1 or more GPUs in your VM. And that's just shown here that we've tested all these configurations, and we can linearly scale the performance of most of our applications as we add GPUs to the VM. So it shows nice linear scalability by scaling up GPUs that way. Sharing mechanisms include NVIDIA Grid, which you see in the bottom left-hand corner and bottom right-hand corner there. So we can dedicate a full GPU to a virtual machine using NVIDIA Grid, or we can share that GPU across multiple virtual machines using NVIDIA Grid. And NVIDIA Grid is a piece of software whose proper name is NVIDIA Quadro Virtual Data Center Workstation 7.0. We call it Grid for short. It's a piece of software that we're going to slot into the hypervisor itself, the hypervisor being the bare metal controller that's serving up resources to different VMs. It's our core operating system, if you like. And this way we can say a set of GPU applications spread across multiple VMs can now share physical GPUs. Maybe they get 1/8 of the memory of the GPU, maybe they get a quarter, maybe they get a half. It's up to you to decide that. We call that a profile. And NVIDIA jointly developed this with us, and it's very much a tested and supported product on VMware vSphere, which is our core data center thing. This gives you all the benefits of virtualization, like isolation, as my colleague Mohan said, workload isolation. That's about securing data that is visible for one data scientist that shouldn't be visible to another, and fast provisioning. And we've done work on performance here that shows that's about the same as doing a direct path I/O type situation. Performance is no worse than doing direct path I/O, which is very close to physical. And how this works is we slot that bottom orange-colored piece of software, which we call a VIB, a virtualization-specific module, into our hypervisor, which we call ESXi here, the green box. But we also depend on the CUDA libraries and drivers being present in the guest operating systems at the top. There are 2 Linux VMs here. And there could be more than that, of course, on this host, but just for simplicity purposes, we're looking at 2. And these 2 VMs believe they have a virtual GPU. They believe they have a GPU to themselves, a vGPU. Just like we virtualize CPUs and we virtualize memory and virtualize disks, to virtualize the networking, we're virtualizing the GPU here with the help of NVIDIA's software. And the manager down in the hypervisor is trading off these 2 VMs against the GPU. And in fact, there's only one physical GPU at the bottom. Now, this could be multiple GPUs here and multiple VMs using it. But the point is, you're sharing. There's no reason you couldn't have just one virtual machine on that host that had entire ownership of that physical GPU if you wanted to. You could dedicate. But if there are opportunities for sharing, you can exploit them this way. And we're showing this little configuration window simply to indicate in the bottom drop box there what types of sharing you're allowing. The numbers immediately before the letters at the end, like the 8s and the 2s and the 4s, indicate how many gigabytes of memory that particular VM is going to get dedicated to it, that memory belonging to a particular GPU. So the way we carve up the GPUs into virtual GPUs is we say each virtual GPU is going to get 8 gigs of the total 16 or 32 that are available on that physical GPU device. So we do memory carving rather than CPU or GPU cycle carving. Everybody gets the right to execute in the GPU. And that's a well-known thing, and that allows you either to share or to dedicate, far left-hand side or far right-hand side. Another technology that we're working very hard on is the capability to have a bank of physical servers with virtual machines running on them. That's the bottom orange box there. And these virtual machines are GPU enabled. They have some form of direct path or other mechanism for using GPUs. The bank of virtual machines on the physical servers at the top, by physical servers I'm representing it with ESXi host here. These do not have GPUs. They're regular CPU-based VMs, but they are clients of those machines that are GPU enabled at the bottom. So you have a client-server breakdown here where you have virtual machines that have no knowledge of GPUs at all, but they might be executing TensorFlow, and they require GPU functionality for a certain period of time, and those instructions will be remoted over the network, preferably a very fast network, remoted over the network down to the orange collection. And in the orange collection, one or more GPU-enabled VMs will be chosen to supply GPU power back to the clients in the green box at the top. So effectively here now, you have a bank of people doing software development in the green area that are making use of GPU power in the orange area at the bottom. And we've done this in our own labs and proven that it's a performant and perfectly feasible, shareable system. So now back to my colleague Mohan again for utilization.
So now we looked at how the GPUs can be shared, but now let's look at some real-world examples and case studies on how this is used, right? So the first one we want to talk about is suspend and resume. So it was mentioned when we talked about NVIDIA Grid that we have a suspend and resume capability. So what does that mean? A VM that's running using a GPU can be potentially suspended, and the GPU can be stolen from it, given to some other server, used, and then given back to it without any loss in state. So that's kind of what this is. So by doing this, this kind of a scenario, what it gives you is the case study we're going to look at next, right? This is a case study where we call a cycle harvesting. So there's a bunch of engineers in a public university here in the US that use GPUs on a day-to-day basis during their daytime. So they are using the GPUs for design and other aspects. Using a VDI, a virtual desktop, they are actually using graphics and the GPU capabilities. And in the night, when they actually, when they actually leave, if you look here, at 8 a.m. they come to work. So their VMs are unsuspended or resumed at that time, so they're able to use it. And then at noon they go to lunch. So maybe an hour or so it's idle. So they're suspended and the GPUs are used. And then at 5 p.m. again they go home, right? And so it's like you have the cycle harvesting where when these GPUs are not used, you're actually using it for batch-oriented processing at a server level. And so that's you, and this is kind of gives tremendous value to our customers where, you know, GPUs are a very expensive commodity, particularly the Tesla GPUs and others. And so by sharing it, you're actually being able to harvest these GPUs when it's not being in use, right? So it's a kind of very powerful use case, right? So we have a case study on it, and then the details are in that link there. We are sharing the presentation, and you can kind of go look at it, right? So the next thing what we did was, okay, now when you do virtualize HPC, you also talk about containers, right? Singularity containers are a very popular mechanism for virtualizing HPC itself. It's seen as a competitor to virtualizing, but it's actually not. So we did a project with Singularity where actually, we want to bring best of both worlds together. So why did we use Singularity containers? As you guys would already know, they are best suited for HPC environments. Docker was meant for microservices, whereas Singularity is meant for heavy-hitting apps like high-performance computing, right? So we chose Singularity. And then what does combining these two give us? So a VM technology has been developed over the past 20 years. You're able to get pieces of hardware, be able to share hardware. In the case of a container technology, you're not able to do the resource management. If you have a container host and then you have multiple containers running, there's nobody stopping the containers from stepping on each other. Whereas if you run the container in a virtual machine, you're able to kind of define what resources that container will get. So that's kind of what. And from a container standpoint, it's got its great advantages in the sense that the entire app is packaged as a file. So you take the best of containers and you take the best of VMs and join them together. So then you get the best of both worlds. So we did that, and then we used Bitfusion that we talked about earlier. So with Bitfusion, we are able to access the servers below, and then the Singularity container is enclosed in a VM, as you see on the top. And then we can kind of give GPU based on what the project demands. So let's say you need quarter GPU for a VM, we can give you quarter GPU. You want 1 GPU, you can get 1 GPU. So this kind of, by packaging all the machine learning stuff within the container and then putting that container in a virtual machine, we are able to, and virtual, by giving GPUs, partial or full GPUs to the container or to the virtual machine, you're able to actually do the resource control that the container lacks, right? And so what did we do here? So what we did was, we did an experiment. So we took a VM, gave it an entire GPU. We ran image processing testing, machine learning with ImageNet, right? What we saw, and then what we did was, we then took the GPU, split it into 4. We gave quarter of a GPU to 4 different VMs, and then we compared the results, right? So what we saw is that we are able to get 3x the number of images processed by the 4 VM combination compared to the 1 VM combination. We're using only the same 1 GPU at the same time, but with 4 VMs sharing that 1 GPU, we get 3x the throughput. So you see that in batch applications, you might not, even though you might be giving a whole GPU to a particular workload, you are not going to be necessarily using the whole GPU. By dividing, we see that we are gaining. But of course, there's going to be some loss, right? When you take 1 GPU and split it against four different VMs compared to 1 VM, there's going to be some slowness. So this is what we did, right? When we studied that, we saw the slowness was 17%. The jobs were running 17% slower than when they were running on one GPU to 1 VM versus 1 GPU to 4 VMs. There was a 17% slowdown. But we saw 3x the images processed. So there's a lot to be gained by sharing, and that's kind of what this shows you. So through this, what we showed you is that sharing is a good thing. A lot of times people think they need an entire GPU, but due to the cost of the GPU and other things, you can actually consolidate within your data center. You can take all the GPUs, put them in a bunch of servers, and then share them across your entire environment, so everybody's able to use GPUs. At the same time, you're able to leverage and get more throughput out of it. So in summary, this is what the main message is we want to share, is that sharing is key to enabling cloud-like capabilities. In the private environment, in a bare metal environment, you don't get this sharing capabilities. By layering VMware on top of your private cloud or your internal data center, you can gain more out of it, and you can get all the agility and other aspects you have in the public cloud in your own data center. So that's all I have. Yeah, go ahead. Yeah, first, yeah. Okay, go ahead. Yeah.
Is there set limitations on just how many VMs you created versus percentage loss in time, or percentage loss in processing? You said you were 17% loss in first. What's the limit? How far would you measure this all the way out as far as how many VMs and the type of problems you were doing?
So we just chose this experiment. We didn't really kind of look at all the combinations. So, but yeah, we just did 2 use cases, 1 GPU and 4 quarters. So we did not really expound beyond that.
In general, in virtualizing alongside Mohan's experiment, there's a lot of work done to see what the effects of more virtual machines on a server would be. And we have white papers on that we can pass on to you.
On the part you were talking about, let's see, where you had the CPUs who had temporary or conditional access to a GPU. Is that, can you do it on the fly, or is that, I don't even know if we got this out.
Effectively, you have to configure the virtual machine at creation time to have its share of the GPU. It's a static thing today.
It is static, but if you can power down the virtual machine, you can add, if you want to change the GPU profile of a particular virtual machine, you just have to power it down and then add a new profile to it.
And this you said is in a paper?
There are papers
Blogs.
on this that we can pass on to you, yeah.
Is the only thing that you need from NVIDIA to do this kind of virtualization a quadro GPU, or do you need some grid GPU thing?
So let me explain that. So you have to buy The grid is a software, and then you have to buy a grid-compatible GPU card. So only certain cards are supported with the grid software. The server-level cards, like the Tesla is supported, for example. So you have to have a Tesla card, Tesla P100, V100, and then you have to have the software that does the division. So you have to buy, it's two different components you have to buy.
Most contemporary enterprise-grade GPUs would support it. Teslas and V100s, those types. Gaming GPUs probably don't.
Any other questions?
When you virtualize the GPUs, you worry about network topology. How do you jump from you virtualizing, but it's not exactly?
Okay, so there are two things, right? First, we talked about the direct path. So the direct path is not impacted by networking. So if a VM is on the same host and then you're actually talking to the GPU, you're going through the backplane, so that is almost like a bare metal. When we talk about bit fusion, where it's going over the network, what we use is Mellanox and others, where we 100 gigabit networks. So we compare 10 gigabits per second performance with 100 gigabits. We do see some improvement. We run all the benchmarks, and we're within 10 to 20% of bare metal by having a high-speed network. And sometimes RDMA could help as well. Yes?
With VMware Workstation and VMware Fusion, what are those things doing when you don't have this grid GPU software?
So those are really workstation level products. What we talked about as ESX is data center level. Workstation is what you put on your laptop, right? Well, it's like a Windows, it's a product for your Windows laptop, and Fusion is a product for your MacBook, right? So those are completely different class of. So what we are talking about here when we talk about is vSphere or ESXi, which are used interchangeably, and they are hypervisors for servers at the data center level.
There is some support for GPUs in Workstation and possibly in Fusion. The product manager sits beside us. We'll ask him when we go back. But I know for sure that I've seen a GPU card that he's working with his Workstation software. But that's another business unit to us. We focus on the enterprise, as my colleague said.
All right. Thank you, guys.
Thank you.